Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at one of my favorite classes of reactions, and that's redox reactions. So while a lot of attention is spent on acid-base or precipitation reactions, when you're trying to find what the most ubiquitous form of reaction is, it's probably going to be oxidation-reduction reactions, more commonly known as redox. These are essentially any reaction where electrons move from one atom to another. And this includes everything ranging from biological metabolism to fuel chemistry, to a lot of metallurgy, and things like including a wide array of materials chemistry and geology. It goes on and on. It really does kind of show up everywhere. And so really when we're looking at these redox reactions, all I'm doing is I'm moving electrons from one place to another. So we can start with some place where it's fairly simple and kind of obvious, where we have something like zinc and copper ions. So here we start with zinc having no charge, copper having a charge. The electrons can then move from the zinc, leaving a positive charge, to the copper. And what we're going to do is typically use our oxidation states that we learned previously to help track the movement of electrons. So any atom that loses electrons is going to be oxidized. So again, zinc starts with an oxidation state of 0, or a charge of 0 in this case, and moves to a charge of 2+, which in this case is an oxidation state of 2+. And any atom that gains electrons is reduced. And the reason why we say that is because the oxidation number goes down. However, there's a lot of mnemonics we can use to help keep these terms straight. So I'm personally a big fan of oil rig. Oxidation involves loss, reduction involves gain. Here we're talking about the movement of electrons. So if you're oxidized, you're losing electrons. If you're reducing, you're gaining electrons. I have actually spent time as an electrochemist who looks at redox reactions. I still have to repeat this to myself almost every time. So don't feel above using a mnemonic. They can really help you out. However, while I prefer oil rig, some people prefer Leo says grr, which means loss of electrons is oxidation, gain of electrons involves reduction. So again, you can either be looking at it in terms of how the electrons are moving or involve it more directly. Loss electrons, oxidation, gain of electrons, reduction. Whichever one you feel comfortable, that's the one you should use. However, let's go ahead and one of the tricky things when we're looking at the oxidation reactions is sometimes it's fairly easy to track the movement of the electrons, such as a case where I'm looking at full charges on individual ions. However, a lot of times it's useful if we can look at those electrons a little bit more directly. And one of the ways we can do this is by looking at our half reactions. So we're going to do is split up this process into two bits. One involves a system losing electrons, and one involves a system gaining the electrons. So if I'm looking at zinc, the zinc is losing 2 electrons as it forms a 2+, and those 2 free electrons. So zinc is oxidized as it loses electrons. Copper is reduced as it gains electrons, as I go from copper 2+ to copper. So any electrons lost from zinc are immediately gained by copper. And so in this case, you should kind of see a similarity to acid-base reactions. For acid-base, what we're looking at is the movement of protons. Somebody gains, somebody loses. You need to have both present in order to have a full reaction. With redox chemistry, somebody gains and somebody loses, but now it's electrons, and they need to make sure that it's always balanced. So whenever you're looking at these half reactions, always make sure that one element loses the same amount of electrons as the other element gains. It has to all come out even. And again, it's this really paired nature that makes it a redox reaction, not a reduction reaction, not an oxidation reaction. They go together. And so one of the ways this embodies is also the way we talk about oxidation and reduction. Because if I have one element that is oxidized, so it loses electrons, like the zinc, it means that I'm reducing something else. And if I'm reduced, like the copper, it means I oxidized something else. So if my oxidation number increases, it means that my element is going to become oxidized, which means it's reducing somebody else. So anytime you find an oxidized element, it'll often be referred to as a reducing agent as well. And the reason why is because the element of interest, so in this case, zinc is being oxidized. It is reducing the copper because it's losing electrons. So that means that somebody else is gaining. So in this case, zinc is being oxidized, but is also a reducing agent. Similarly, if your oxidation number decreases, like copper's, it means you're being reduced and you're oxidizing somebody else. So you're gaining electrons, which means you're stealing them from your neighbor. So copper is an oxidizing agent in this case, and it will be very dependent on the individual reactions and systems. So let's go ahead and look at something that's a little bit more complicated. So here's two good reactions. We can try and identify the oxidizing and reducing agents by first looking at our oxidation numbers. So one of the first cool reactions we can look at is lithium plus manganese oxide. This may feel fairly inconsequential until you realize that this is one of the reactions powering your battery, powering your phone, as this is a lithium ion battery. You have a lithium solid, you're reacting it with either a manganese or cobalt oxide to generate a complex. So this is how we move electrons in your phone. So in this case, lithium starts with an oxidation state of 0. Oxygen starts with 2-, manganese at 4+. Our products, lithium is now 1+, oxygen is still 2-, and manganese is now 3+. So now we have to figure out who gained and who lost. So the lithium ends up increasing in oxidation number. It's being oxidized, which means it's a reducing agent. Similarly, manganese, its oxidation number decreases, it's gaining electrons, which means it's an oxidizing agent. Let's go ahead and look at another kind of fun reaction. This is called a water gas shift reaction. It's one of the ways you can make renewable hydrogen gas. You can combine carbon monoxide, which is often an unfortunate byproduct of a lot of processes, and as you may know, quite toxic. If you react it with high temperature steam, you can make carbon dioxide, still not good, but less toxic, and hydrogen gas, which is a potential fuel. In this case, oxygen starts with a 2- oxidation state. Hydrogen starts with a 1+, and carbon picks up the remainder. It's 2+ in this case. In our product, hydrogen is now elemental. It is an oxidation state of 0. Oxygen, still 2-, not really changing, but to keep that extra 2- on the carbon neutralized, carbon is now a 4+ oxidation state. So carbon increases oxidation state. It is being oxidized. So that means that our carbon dioxide is a reducing agent. Our hydrogen, its oxidation number is being reduced. So it's gaining electrons, and it is an oxidizing agent. So here's one of the classic confusions of redox chemistry, but also its power, that everything comes in pairs. Something is reduced, something is oxidized. It makes it really easy to mix up. So try and get some practice, remember your oil rig, and you should have a lot of success. However, so far we already are using balanced chemical reactions. Next time, we're going to try and figure out how you can try and balance a chemical reaction yourself. Until then, take care.